So thank you all for being here. As you can see, this is trenching and excavation competent person training. This sets out to make you aware of the hazards and able to make sort of inspections and just be able to make the right calls as it comes to trenching and excavation. So again, the objectives of this session, you'll be able to recognize trenching hazards, choose protective systems, getting the right one for the right job, and identifying those hazards. So introduction, just breaking down sort of the definitions and things. Excavating is recognized as one of the most hazardous construction operations. A lot of the standards you'll see here will be in the 1926, the construction standards, but they will still apply for you. And I'm aware that you contract a lot of these out, but you still work in them. So the competent person training is sort of what makes you aware of those hazards and know that you're in a good spot here. It's important because the fatality rate for excavations is twice that of construction as a whole, and cave-ins are the number one hazard of what you saw earlier. More likely to result in worker fatalities than other excavation-related accidents. 90% of all violations related to the lack of cave-in protection. And during inspections where these violations were cited, the excavations were nearly vertical. Again, you saw that in the other one where it's just they think a trench. An excavation is any man-made cut, depression, or trench made by the removing earth. A trench is a narrow excavation that is deeper than it is wide, no greater than 15 feet wide at the bottom. Trench walls will eventually fail. Need to assume that will happen. These are the most cited by OSHA. So number one is going to be employee protection and the protective system use or lack thereof. The second will be egress. We'll cover that in here as well, and how often you have to have entry and egress from trench excavations. The failure to inspect by a competent person is the third most, and on here. So what is a competent person? A competent person identifies trench hazards. They are authorized to take prompt corrective measures to eliminate hazards. They are knowledgeable about soils, protective systems, and OSHA rules. They are responsible for daily trenching inspections and determine which protective systems to use. So daily inspections of excavations, the adjacent areas and protective systems, they'll be made by a competent person for evidence of a situation that could result in possible cave-ins, indications of failure of protective systems, hazardous atmospheres, or other hazardous conditions. An inspection will be conducted by the competent person prior to the start of work and as needed throughout the shift. Inspections shall also be made after every rainstorm or any other kind of hazard that will increase occurrence. And these inspections are only required when employee exposure can be reasonably anticipated. So where the competent person finds evidence of a situation that could result in a possible cave-in, indications of failure of protective systems, hazardous atmospheres, or other hazardous conditions, exposed employees shall be removed from the hazardous area until the necessary precautions have been taken to ensure their safety. Trench inspections, you'll want to do those before work starts, throughout the shift, and again after a change in the elements or soil stability. You want to, again, inspect for the evidence of possible cave-ins, indications of failure of protective systems, and potential hazardous atmospheres. So some statistics here, over 40 workers die and 1,000 are injured per year in these. It's included in OSHA's Fatal 4 for construction. So the common causes are no protective system, unsafe entry and exit, failure to inspect, and unsafe spoil placement, and the lack of a competent person. So for soil stability, grain size, small is better. So think of a grain of sand, that's small, but in terms of soil, that is large. So we'll go into the types later on, but just as a rule of thumb, the grain size is small. So water saturation, that changes it. That's why after a rainstorm or whatever, that changes the conditions, and another inspection will need to be done. The cohesiveness, how well soil sticks together. There will be a bunch of tests that we cover in this later on to determine that. And you'll hear a lot in this about the UCS, the unconfined compressive strength. That just is a number for how easily the soil will shear. So there's a tool later on that we'll talk about that measures that and actually puts a number on there. So this here is a case study of a local case of a incident involving so a lot of eyewitness and family accounts here of obviously all these trainings and things that we do, a lot of OSHA standards, all that. You always hear that these things are written in blood. So this is just kind of a local case that reinforces that and shows how dangerous these sorts of things can be. At the bottom of this, it accounts how when they arrive for the rescue, everybody's upset. They're trying to get them out. They're trying to dig them out. They're trying to do the work after, the incident's already been done. So you want to get ahead of these things so that you're not scrambling afterwards. Soil characteristics. Soil that remains in clumps when excavated is cohesive. Soil that breaks up easily and does not stay in clumps is granular. The cemented soil is highly cohesive and it will not break with finger pressure. And cohesive soil high in clay does not break apart into particles, can be formed. So one of the tests that we'll talk about is just as simple as like a thumb test, things like that. You can tell these things pretty easily. It's nice to have a tool that we'll go over, but a lot of these things you can know pretty well off the bat and know to look for yourself if you're down there. So the different types of soil and the classifications. The classes are stable rock and then soil types A, B, and C. So each type requires a certain protective system. You need the right tool for the right job, as you do with all things. And a competent person is the one who will determine this soil. So here's sort of a graph that shows how the soil can be made up in a variety of compositions here. It can have any percent of the three of here. At the top, you'll see clay here. It can be type A, B, or C soil. So just because, even if it's 100% clay, and we'll go into this, but even if it's 100% clay, it can still even be a type C soil because of, a variety of factors around it. So we'll go into that more in depth. So for soil types, type A, it is the most stable soil type that USC, I think it's UC, that number that we were talking about earlier, if it is 1.5 tons per square foot or more, then it'll be a type A. And these are, again, as I said about clay, even if it's 100%, it will not be type A if it is fissured or the soil is subject to vibration from heavy traffic, pile driving, whatever, or the soil has been previously disturbed, or the soil is part of a slope. So for that reason, we don't consider any soil types on campus a type A because obviously all of the construction building that's been done here, all of that's been disturbed in the past, right? So we'll at least consider all of it at least B or C. So just go ahead and jump ahead here and I'll go back. There was a question yesterday and I had to go back into our program to make sure, but where it says here that all soil on campus, see, that's not necessarily the case. If you want to consider it that way and you want to go above and beyond, that's great. But you don't have to take all the measures and consider the type C as it says here. So kind of disregard that and we'll kind of go back into type B here. So type B is cohesive soil with a UCS greater than 0.5 but less than 1.5 tons per square foot. It will be granular, cohesionless soil in its previous soil. So it can be a quote unquote A soil that is fissured or subject to vibration, or dry rock that is not stable. So type C here is cohesive soil with a UCS of less than 0.5 tons per square foot. It is granular soil, including gravels and sand, submerged soil or soil with seeping water, unstable submerged rock, sloped layered system of material, or steeply sloped material. The soil mechanic. The unit weight of soils will refer to the weight of one unit of particular soil. The weight of soil varies with type and moisture content. And 1 square yard can weigh more than 3,000 pounds. So that's why these cave-ins are extremely dangerous, because you don't know how heavy or whatever this may be, and it can trap you. It can suffocate you even without getting to the nose or mouth, right? It can suffocate you by closing in your chest or whatever. Consequences of a cave-in. Soil is dense and heavy, as I said. It can entrap, bury, or injure. Suffocation. Again, their soil prevents chest expansion, and the worker becomes immobilized.
Ethan, there's a question. How long of a period is previously disturbed?
For my understanding of it, that's why we have to consider all of it, at least type B, right? Because when it's a soil on campus, it's been disturbed, right? That's why we can't consider anything type A and only take type A measures on things on campus. What is a cave-in? A cave-in is a separation of soil or rock from the side of a trench. The material falls in, sudden movement, and the gravity pushes soil downward and sideways. So there's two diagrams here that show sliding. It can come from the bottom, or toppling. It can break apart and come from the top there. So signs of soil distress. You can look for fissures or cracks in the trench wall. The wall of trench slumps or falls. The soil bulges or heaves. The excavation's edge sinks. Material ravels or trickles into excavation. So these are sort of the visual things that you can see and be aware of, that this can happen, which if you have the protective measures in place, you shouldn't be seeing any of this. But again, these are sort of the hazards that you need to be aware of with these. Soil distress and the conditions. Nearby vibrating machinery, so nearby moving heavy loads, seeping water or rain, or hot, dry weather. So high traffic areas, and think about in construction, all the heavy machinery that can be around it. Those are the sort of things that you need to be aware of that can distress soil pretty easily. So these are the soil tests here. There will be slides breaking down each of these, but the tool that I was talking about, I don't know if you see my mouse here, but the second one, the pocket penetrometer, it's this on the side here. This tool here is made for these. So that's the tool that I was referring to, and we'll go into how that works. Again, a lot of these are things that you can do if you're just working down there. If you're not the one that's making these classifications, these are things that you can do still while you're down there, just to have that sense of security and know what you're doing down there. Just as easy as a visual, that tool, the thumb penetration test, the plasticity test, and the dry strength test. So visual test. To determine qualitative information regarding the excavation site, consider the soil adjacent to the excavation, the soil forming the sides of the open excavation, the soil taken as samples from excavated material. So you need to not only consider what you can see, like on the wall or the slope or whatever on you, but the adjacent soil as well. So visual test. Observe the side of the open excavation surface area adjacent to the excavation. Crack-like openings such as tension cracks could indicate fissured material. Observe the area adjacent to the excavation and the excavation itself for evidence of existing utility and other underground structures, and to identify previously disturbed soil. Small spalls are evidence of moving ground and are indications of potentially hazardous situations. So here's this and how it's used. If you can tell on there, the little red ring at the base there, and I believe the next slide has a better kind of depiction of that. This is the tool that'll actually give you a concrete number if you want it to decide what type the soil may be. It's a direct reading spring operated instrument. It's used to determine that UCS. So we've been talking about that number and the strength of the soils. So once it's pushed into the soil, the indicator sleeve displays the reading. The instrument is calibrated in either tons per square foot or kilograms per square centimeter. All the readings we've been talking about has been the tons per square foot, and they do have error rates, but it's nice to have a tool that's made for that. So this is the better picture you can tell here with the number readings there, and how much it pushes in. So you want to push the ring all the way towards the handle, and you'll push the shaft into the soil up to the red ring. Hold the barrel so that you're not interfering with the spring inside the barrel. Read the UCS at the bottom of the red ring slip. So again, it shows sort of the criteria there on what the numbers. If it's greater than 1.5, it'll be A. If it's 1.5 to a half, it's B, and then if it's less than a half, it's C. Oh, got it. Okay, thank you there. So the thumb, again, a lot of these tests are for you as someone who just ends up working down there. You're not doing the classifications, you're not doing the actual digging, but you're working down there, and you want to make sure that you're protected. Another one of these is just a quick thumb test. So you just get a large clump of undisturbed. You attempt to penetrate it with the tip of your thumb, and then obviously with just how much force lets you know, relative how much cohesion it has there. So with great force, it's type A. It'll penetrate to the full length of the thumbnail. With type B, and it will penetrate easily several inches and can be molded with light finger pressure on type C. So another easy to run, you can do it yourself without any tools, is a plasticity test. If you roll it up into a little ball, and then you kind of roll it into like a worm there, like you can see in the picture, and you hold it by that base. If it remains suspended without tearing, then the soil is cohesive. So just another quick one that anybody can do there. This video just kind of covers everything that we've been over, so we'll go through that. So again, this is a construction reading of the requirements here, but it just kind of covers some other things to be aware of. So if you're in traffic areas, reflective vests are required. No workers need to be underneath loads handled by lifting or digging equipment. Barricades, stop logs, or hand signals for mobile equipment operating near excavations. The trench protective systems, so these will provide full worker protection from cave-ins, except excavation completely unstable rock and in less than 5 feet deep, and the competent person determines no. So these should be able to protect without failure. They should be engineered. They should be bought within these OSHA standards and will have no chance of failing. So these protective systems will be sloping and benching, shoring, and shielding. See here. So first we'll go over the sloping. That's the angling of the wall. It will angle the walls of the trench in the form of an incline and protects from cave-ins. And the angle will be determined by the soil type, environmental conditions, all those that decide what the soil type is. And then benching is excavating the sides of the trench in a series of horizontal levels or steps, usually with vertical or near vertical surfaces between the levels. So it just makes a series of steps. And then again, the classification of the type will decide, what you can do and what angle that you'll. There's a lot of math there, but just kind of the best way to think of it is type A, it's 3 to 4. Type B, it's 1 to 1. Type C, it's 3 to 2. So you'll want to angle flatter out for the more coarse and less cohesive soils. And that just kind of breaks it down again and shows angles there. So for shoring, removal will begin at and progress from the bottom of the excavation. Members, they will be released slowly so as to know any indication of possible failure of the remaining members of the structure, possible cave-in from the sides. And backfilling will progress with the removal. So the advantages to these hydraulic shoring systems are that they're light to be installed. They will be gauge regulated to ensure even distribution of pressure along the trench line. They can have their trench faces preloaded to use the soil's natural cohesion to prevent movement, and they can be adapted easily to various trench depths. So all shoring should be installed from the top down and removed from the bottom up. It should be checked at least once per shift for leaking hoses and cylinders, broken connection, basically anything that you're looking for with all of your other hydraulic equipment. You don't want to just completely trust hydraulic equipment, right? You want to check on those things the most that you can so that you make sure that they're still going to be working for you. So shielding, I think you see this the most. It kind of allows you more working space around it, right? With the use of these withstand forces of a cave-in and protect employees within. These are pre-manufactured or portable. They can also be built on site, but they must be built to OSHA standards, right? But a lot of these things will be portable to be brought in and they'll be dropped in. So with trench boxes, they're not for height extension. They're used with sloping and benching. No one is permitted inside when moving, and the top of the box must be 18 inches above the surface to ensure that there's no falling in, caving in from the top of it, right? So this shows shielding systems along with some shoring there. The shield systems are not subject to loads exceeding their capacity. These, along with everything else, you want to make sure that you're reading the tags on those to make sure that you've got the right one for the right job, right? They're installed to restrict lateral movement, employee protection provided while entering and exiting shields. No employees entrenched during installation or removal of these shields. There's a picture here. It's not showing you a lot, but it's saying what's wrong here, right? So as you can see, obviously he's got his back to a pretty well vertical wall there. There's no shoring, there's no protective measures there, but also you can't see up and down it, but at least by looking at this picture, you can tell that there's no means of entry or egress. So in the case of an emergency or just any case at all, right, there's not enough ways to get out of there. So this is UK's inspection permit here. Kind of may remind you of a confined space permit. So if you're going to be doing any kind of excavation, trenching, that sort of thing, it sort of just walks you through the process. First you're going to classify that soil, then you're going to break down what you're doing to protect it, whether you're doing sloping, shoring, shielding, whatever. It goes through a bunch of questions that you need to ask. Again, it's like the confined space. So all the things that we teach in the training that we want you to do is kind of another one-stop shop that makes you check the box on a lot of things. Say, I marked the underground utilities. These are the ones that we're aware of. This is what we're doing and all that. So for hazardous atmospheres. So again, we can kind of relate this to what we do with the permit required confined spaces, right? At excavations near sewers, landfills, and other potentially hazardous atmospheres, you want to be testing that atmosphere. You want to use those gas meters used. You want to ventilate. It's a good way to mitigate that hazard. You're going to use appropriate PPE. If it's some sort of atmosphere that requires a respirator, you're using that. You're using the right one, right? Maintain rescue and emergency equipment on site. So this breaks down, again, relating it to the confined space. So if there's hazardous concentrations of airborne contaminants or oxygen deficient atmospheres. The compliance with UK confined space program is also required there. So employees shall not be permitted to work in hazardous or toxic atmospheres. These include atmospheres with less than 19.5% oxygen, combustible gas concentration greater than 10% of the lower flammable limit, concentrations of hazardous substance that exceed those specified in the threshold, so like H2S with those values for airborne contaminants established by the ACGIH. Obviously, you don't ever want to let any of these things get anywhere close to like a 10% on the LEL. You don't want to let anything get close to 19.5% oxygen. If you have the sort of monitors and you're off of just the normal level of these things, that should ring a bell, but these are, the numbers that are really gonna alarm you with those. So falling soil or equipment. You want to keep material, soil, and equipment 2 feet from the edge. You want to use retaining devices. You don't want anything to fall in from the top, right? It's just like anything else when you're working below and there's someone working above you at heights, or there's just anything going on above you. You don't want to have that risk of things falling on you. So trenching and other excavations, you will want to consider the possible effects on adjacent structures. So the excavations might endanger the stability of buildings, walls, other structures. Sidewalks and pavements must not be undermined unless supported to prevent collapse onto excavation work. Use shoring or bracing to ensure the stability of nearby structures. And there'll be no entry where workers below adjacent footings unless shored or stable rock or approved by a project engineer. So entry and exit, we talked about that. Trenches are 4 feet deep or more, then you must have an entry or exit within 25 feet of a worker. There should be no place in the trench excavation where a worker can get to where there's not an exit of 25 feet away. So these will include ladders. You want ladders lining all up and down, stairways if you're doing that, or sloped ramps. Whatever. Other trenching issues here, you want to mark all underground utilities. Again, that's another thing that the permit lines out for you. And whether you're using drawings to do that, you're calling 811, you're using a third party to locate those. You want to make sure that you're aware of what's under there. You don't just want to go head first with a shovel, right, and blow something. You stand away from lifting and digging equipment. Wear hard hats. Obviously, you don't want to be struck by anything, and you want to use warning systems or barricades. You want it to be abundantly clear to people around you that they need to stay away from this. One wrong step, you can step in. You just want to have proper signage and all that. Some more trenching issues, use fall protection systems if needed in those cases. You want to protect people from, again, walking up off the side or people doing adjacent work. You don't want there to be any way that people can fall into these. Again, no work above other workers. You don't want people to drop something. And then obviously we just want to monitor excavation work at all times. So key points, this is just kind of a conclusion slide here. You want to be aware of all the hazards associated with working around trenches. Cave-ins will occur suddenly and can entrap, bury, or injure. And always use protection systems.